So this is our objective. By looking at the trajectories of the linearized system around the equilibrium point, can we infer something about the behavior of the trajectories of the nonlinear system 1, right? So to answer this, we'll need the following theorem. So it's known as the Hartman-Grobman theorem. So what does it say? If the linearization model has no eigenvalues on the j omega axis, right? That means all the eigenvalues are either this side or that side of the j omega axis, right? That's what it means. On the j omega axis, then there exists then there exists an open set and a homeomorphism H from U to R such that H maps trajectories of 1 to trajectories of 2. So wordings have to be more clear. Yeah. Furthermore, trajectories of 2 H of x not equal to 0. Further, H preserves the parameterization of time. Anyway, we are not going to do the proof of this theorem. It's a very lengthy proof, but we'll try to understand the implications of this theorem. Okay, so if you pictorially see, so I have some nonlinear system. Okay, say this is the equilibrium point. Okay, and then there is some coordinate system. So I've purposely drawn it skewed so that it captures the nonlinear system. So this is a system 1. Okay, and then you have some trajectories, going something like this. So you have a something like a saddle stable node. Okay. Now what it says is, you can find a homeomorphism which will straighten out these coordinates, right? These are some nonlinear coordinates, okay? So this homeomorphism will straighten it out, right? And what you see is that in the straightened out coordinates, which is a linear coordinates, which is the linearized model. So this is model 2, right? What you see is the trajectories are qualitatively same. So if you, the main hypothesis of this theorem is that you should not have a eigenvalues on the j omega axis. That means there should be no eigenvalue with a zero real part, okay? In fact, such equilibrium points are called hyperbolic equilibrium points, but let us not use the terminology. So as long as you don't have any eigenvalues, okay, none of the eigenvalues are on the j omega axis, then there exists a homeomorphism. There exists an open set. So this is some kind of open set, right? So you can talk about, say this is some open set U, okay, in the neighborhood of this equilibrium point, such that the trajectories of this nonlinear system are mapped to the trajectories of the linearized system, right? And so the homeomorphism maps the trajectories 1 to trajectories of 2, right? That means this trajectories, right, when you look in the linearized system, right, they are straightened out, okay? But the most important thing is the nature of the trajectories remains the same. So what you see here, all the trajectories are going to the origin, right, or the equilibrium point. The same behavior is preserved here, right? So the so what we are trying to see, what gets preserved is that if it is a saddle here, sorry, a stable node, right, then locally this also is a stable node. If you do linearization, if this turns out to be unstable node, this also will be an unstable node. If this turns out to be stable focus, this also will be stable focus. If it is an unstable focus, this also will be unstable focus. If it is a saddle, this also will be saddle. The only case where it breaks down is if it is a center. Okay, if you find it is a center, what is a center? Where the eigenvalue has zero real part and purely imaginary eigenvalues, right? If it is a center, you cannot comment anything about the local behavior of the trajectories for the nonlinear system. That means the higher order terms which you neglected in the Taylor expansion, they play a role, right? For all the other cases, it is okay to neglect the higher order terms to infer the local behavior of the equilibrium point for the nonlinear system, right? But the whole thing breaks down when you have a center, right? So that is the first takeaway of the theorem, right? And so I'll bring out all the, what all it, some kind of remarks from this theorem, right? So this is the first theorem, first remark. Second is more, we'll see more about this H and the flow, okay? So the first point is clear, right? So always you have to be careful about when you do linearization. If you end up with even 1 0 eigenvalue, that's it. You cannot comment anything about the nonlinear system based on linearization, right? Either if it is this side or that side strictly of the j omega axis, yes, you can comment, right? But not when it is on the j omega axis, right? So you see, we don't use words like marginal stability, nothing, okay? So we want to be very clear. You either comment, or when you are on the j omega, we say we cannot comment. We don't have any terminology for that, right? Right. Second is, so we already have learned something about the flows, right? So let here, so for the nonlinear system, let the flow be phi t x, okay? And for the linearized system, let the flow be psi t of x, okay? Now let us see what this homeomorphism is doing, right? So you have a U which is a subset of Rn, right? Now this gets mapped to Rn only through the homeomorphism, okay? So you have this flow here, okay? So yeah, so from here to Rn, you go via this flow, right? On this nonlinear system, you have the flow. How do you go from one point to another point? Using this flow, right? You take a point x and fix some t, right? You want to know where it goes in, say, 10 seconds. You just operate this on that, right? I mean, if you want to give have a example in mind, the best example is for the linear system, right? The flow we wrote. You are already familiar with this. You give an initial condition and you supply some time t. You want to know after 10 seconds where does the state go. You use this formula, right? You have an explicit expression for the flow here, right? So this flow will take you from U to, again, points in this U itself, right? So I mean, maybe it is some open set of Rn. Okay, I'll just write it here Rn. Right? This is for the linear system. So this is the non-linear system. So I'll just write 1 here, 2 here. This is a non-linear system, this is linear. How do you go in the linear setting from one point to another point? Through this flow. Right? Yeah. Now, because there is a homeomorphism from here to here, right, what I can write is that phi t, right, of x goes to this space by h, right? So h of x is same as, right, or I will do the other way. So anyway, t is fixed. Some t is fixed. You agree? What is this relation giving you? You have a flow here, right, in this space. Through h, you map this curve to this space here, which is same as you have a point here x. First you go here through h and then apply the flow on that, right? You see that? So what did I do? So you have a curve here in this space, nonlinear space. Through h, I mapped it, the whole curve, to this space, right? Which is the same as, what you do is, you map the point here, h of x, right? And then you go along the flow of the linear system, right? So in other words, what this diagram says is that, this relation says is that this diagram commutes, okay, or this square, or whatever we say, this diagram, or so you want to go here, you either go like this or you go like this. That is what, Rn, yeah. This also. Yeah, thanks. Right? So you take a point, right? You go along the flow and apply H, or you apply H and then go along this flow, right? So this is what it says. Now, let me just cross check whether everything we have done is correct, so that, yeah, perfect. Okay. So this relation says that this diagram commutes. Okay. So maybe if I want to give a better picture, so this is a non-linear system. This is a linear system. This is my homeomorphism. So I have some x, then I go flow or the trajectory for some time t, right? And this whole thing I map here, right? Through this homeomorphism, this whole curve gets mapped to some curve here. Or I just map this x here, right? And then go along the flow of this system. They are the same. So in the left hand side, you already have a flow or the trajectory. You just mapped all the points of the trajectory here, right? You got a curve here. A curve gets mapped to a curve, right? In the right hand side, what you did, you took the initial condition, you mapped here and then went along the flow of the linear system, right? So this theorem says that both are same. That means this diagram commutes. Okay, so you take a point, you go to this space and then go along this flow, or it is the same as you flow in this non-linear system and map the whole thing to the linear system. They are the same, right? But be careful, it's all local, U. Okay, it's in a, how big, how small, we don't know, but there exists some open set. Okay, some open set over which there is a, you can find a homeomorphism. It only says existence of a homeomorphism. It doesn't tell you how to find that homeomorphism. Okay, in fact, Professor Umesh was telling that in the course we'll learn how to actually construct that H. Okay. Now we can do little more. Why? We know already this phi of this psi of t, because it's the flow of the linear system, right? So this is nothing but because the flow of the linear system is exponential, right, of a t acting on the point. We can still do something more. What is that? H is invertible, right? So I can write okay. So you see, you know this, right? You know H, you know H inverse, you can get the flow for the nonlinear system, right? So locally you can map flow from here to here to here, right? So in essence we are mapping trajectories of the nonlinear system to the trajectories of the linear system. They may be distorted, they may be skewed, okay, but the behavior is invariant. So what was saddle here, saddle stable node will remain stable node, unstable node will remain unstable node, and so on, except when the situation is at the center, right? So that is the takeaway from this theorem. So we will see one example what can go wrong, right? The same first order. Okay, so x equal to 0 is equilibrium point, right? Your A matrix is 0 here, right? So the eigenvalues of A is 0, right? And so therefore 0 is sort of, actually we don't classify this center, saddle and all for other than second order system. Those terminology is only for second order system. You cannot extend it to third order, fourth order or any other, right? But we have a zero eigenvalue, right? So just let us just write this, right? Now, as I said, for the linearized system, so I have x naught is equal to 0, which means x of t is equal to x naught for all t greater than or equal to 0. This is the inference you will make if you believe in the linearization, right? But we know this one for the nonlinear system, as is this is the equilibrium point, right? All trajectories will converge to that, which contradicts that the only solution to this linear system is the initial, the initial condition. It will identically stay at the initial condition, right? So you see, you are trying to infer a behavior around the equilibrium point of a non-linear system based on linearization when the linearization has a zero eigenvalue, right? So you cannot do that. Okay. So let us take an example when you can do it, right? Or I'll give a second order example. What can go? Yeah, I have an example. Epsilon is some parameter. If you do the linearization, the A matrix, so it has only, so the only equilibrium point is 0, 0, 0. So the A matrix is 0, minus 1, 0, right? The eigenvalues of A are plus or minus j, right? And okay. So, well, what does this mean? The x equal to 0 of linear system is what? Center. Okay. And you cannot be tempted to infer the same for the non-linear system, right? Because the non-linear system, what will happen? If you draw the phase portrait of this, so it will be a stable focus. The sense, the way I draw this is, if you want to know the sense, take any point, right? Along the x1 direction, it is positive. So this is this arrow, and along x2 dot, x2 is positive, x1 is positive, right? So this whole thing is negative, negative. So it will be all negative along the y component. So the resultant is this. So your sense of direction is this, right? So it will spiral to the origin. So it is a stable focus, okay, which is not what you got from linearization. Right? If you swap sign of epsilon, you will get a unstable focus. Okay. So these examples will tell you, how the information obtained by linearization fails when you have eigenvalues on the j omega axis. Now, yeah, we also saw that the eigenvectors, right, are invariant subspaces, right? That means if you start an initial condition on the eigenvector, right, on the in the linear setting, you have those vectors, right? So you take any initial condition on any of the eigenvector, the flow will be along that. Either it could blow up or it could go to origin depending upon the eigenvalue, right? Now question is there something like that for the nonlinear system? Because there is no notion of eigenvectors, eigenvalues for the nonlinear system. But the question is there something like that, right? And the answer is yes, we have something like that. So the question was, is there kind of eigenspace structure for nonlinear system? Okay, so we have that, but again under what conditions is exactly the given by the Hartmann-Grobman this, right? So we'll define two sets. So I have this initial condition, S stands for stable, okay. So W x naught S, it is a set of all points such that the flow approaches 0 as t tends to infinity. And similarly I have something W x naught, U stands for the unstable, where all points x such that the flow approaches 0 as t tends to minus infinity, right. That means in negative time the solutions approach the origin, okay, or in positive time they blow up. Okay, actually we cannot say blow up, so that's why we have to be careful. So rather than saying blow up, you say that in negative time they approach the origin, right? So for example, you can think of something was escaping out, right? But if you come back in time, it is approaching the origin. In positive time, it is diverging, right? You see that, okay? But this is positive time, okay? Whenever we represent the orientation, it's all in positive time. But in backward time, you are flipping the right hand side of your differential equation. So that means in backward time, this is actually converging to 0, right? So that's how this definite. So not converging doesn't mean it is blowing up to infinity, right? So to explain that, you could have a situation. In fact, I'll do that shortly. So you have some 3 equilibrium points, okay? This may be unstable, say unstable focus, and this may be a saddle, right? Unstable focus means what? Trajectories will spiral out. It doesn't mean they are blowing up to infinity. It could happen that they could be going and approaching the other equilibrium point, right? So you have to be careful. If it is not converging, it doesn't mean it is diverging to infinity. It may be going away to and approaching some other equilibrium point, right? So if we had made this mistake, we would have written that phi t of x tends to infinity as t tends to infinity. No, okay? That's why we did not use that. We said phi of tx goes to 0 as t tends to minus infinity. So in negative time, it is approaching origin, right? Which is what I explained in this picture. So I don't have to, worry too much what happens to this trajectory as t tends to infinity, right? So having defined these two sets, right? Now these are kind of invariant, nonlinear version of invariant subspaces. right? In the linear system, we saw that eigenspace were invariant. So this sets that I have defined, right, they are kind of non-linear versions of the invariant eigen subspaces, right? In fact, this set is called local inset, and this is called local outset. Inset because they are approaching the origin, outset because they are going away from the origin, right? So now how do I connect this to the invariant eigenspaces? Well, that is captured by the following picture. So, so I have this linear system. So let ES and EU be the invariant subspaces, eigen subspaces, right? You can find this. This will be just the span of the eigenvector corresponding to the negative eigenvalue. This will be the span of the eigenvector corresponding to the the positive eigenvalue, right? That is why we use here unstable, this is stable. So what is the connection between this and these sets, right? Well, if you don't have the eigenvalues on the j omega axis, right? None of the eigenvalues are on the j omega axis, then the picture is like this. Okay, so this is Ws x naught, this is Wu, okay, and then so locally this will be Es, right, and then so Es and Eu are tangent spaces to Ws and Wu locally, right? So that is the takeaway. That is the, what do you mean by non-linear versions of the subspaces? Okay. Again, how do you find these sets and all is something which we cannot do analytically. I mean, maybe Umesh will tell some techniques to get hold of that sets. Okay, why do we need the Wxs? There is something beyond, this explanation. So you have a nonlinear system, you have an equilibrium point, right? And you have some other equilibrium points also, right? So you want to find what is the domain of your equilibrium point of interest, such that if you start from any initial condition in that domain, you will reach the equilibrium point of your interest and not escape to some other equilibrium point, right? Because that is very important, because then you know how much perturbations it can take, and or where should I initialize my system. I want to initialize my system such that it goes to the desired equilibrium point and not to any other equilibrium point, right? So that is captured by a notion called domain of attraction. Okay, so I think Umesh will be dealing more with that domain of attraction, right? So this is the fallout of Grobman-Hartmann theorem, right? So you have some nice properties as long as you have no eigenvalues on the j omega axis, but if they are off that, then you have some nice, you can do lot of local analysis by doing the linearization, right? So I'll just give one more example. So can you calculate all the equilibrium points? It's very obvious origin is equilibrium point, because if you plug in 0 here, 0 here, 0 here, then the right hand side is 0, right? Certainly 0 is the equilibrium point, but there are other equilibrium points also, right? For example, x2 is 0, right? Once x2 is equal to 0, x1, 1 minus x1 square equal to 0, which implies x1 equal to 0, right? And x1 square is 1, which means x1 is plus minus 1. So the equilibrium points are 0, 0, right? 1, 0, and okay. So let us mark this on the x1, x2 axis. So you have 1 here, you have 1 here. So this is minus 1, 0, this is 0, 0, this is 1, 0. So let us do the linearization, okay. So yeah, so if you do the linearization about 0, 0, I will not go into the computations, but you can just check. This happens to be saddle, okay, and this too happens to be either stable focus or node depending upon this delta value. You see that if you do linearization, this delta comes in the A matrix, right? So depending upon the magnitude of delta, in fact, for delta equal to, say if you put delta equal to 9, you will get stable node, right? So I will simply write stable node or focus, both of them turn out to be either a stable node or stable focus. It cannot be this is stable node and this is stable focus. No, either both will be node or both will be focus. Okay. So this information is completely from your linearization eigenvalue. That's it, right? So, what will be the global picture, right? So stable. These two are stable, say focus, right? So any trajectory in the vicinity of the this one will approach this. Okay. So how will the picture look? The phase portrait look? So let me draw that. Yeah, we need this also, the eigenvectors here. So which one is yeah, this is the eigenvector corresponding to the unstable, positive eigenvalue, and this is corresponding to the negative eigenvalue, right? So yeah, what will happen? So you can see that even though I am not drawing the phase portrait, one can sort of guess what will happen. Say you perturb somewhere here, right? This trajectory will come and spiral and go here, right? If you then yeah, so this side will be something like that. Yeah. Okay. Some of the points, right? So if you perturb here, they will go like this, and this will some of those. Yeah, you need to actually draw the phase portrait, but I'm trying to give a yeah. So this goes and yeah, some of these trajectories, they will go like this and they will converge. Okay, and similarly you can expect something like this. Okay, so what I want to say is, if a trajectory is not approaching this equilibrium point, it doesn't mean it is blowing up to infinity, right? So you see, even though this is not approaching this equilibrium point, it is approaching some other equilibrium point. this is a saddle, right? So there is a direction in which the trajectories, in fact, all the trajectories are diverging except the one which is on this stable, the eigenvector corresponding to the negative eigenvalue, right? So only this will go to the origin, but all others are repelled away. Repelled away doesn't mean they blow up to infinity, but they go to some other equilibrium point, right? So to a great extent, we could piece together the phase portrait without actually constructing the phase portrait by using the linearization tools for the only reason that none of the eigenvalues are 0, right? So we are sort of crudely able to piece together the global picture, right? Even just using the linearization tools, right? So that is the power of linearization, but as I said, it will have limitations, right? So yeah, please, any questions on this example? We can now we saw equilibrium points, right? What other behavior can nonlinear trajectories can, exhibit? Okay, we already saw in the linearized case, right, the closed orbits for the pendulum system, right, near the downward equilibrium position, it corresponds to oscillations, small oscillations. Small oscillations corresponds to closed orbits in the phase plane or the phase portrait, right? So is there something for the nonlinear system? Okay, so we'll see that. So by the way, in this example, if delta is negative, then this will become unstable focus. Okay, the saddle I think will remain as saddle. These two will become unstable focus. So the other interesting trajectories that you can see in nonlinear system is periodic solutions. Of course, periodic solutions are there in linear system also, right? But there is something unique in the nonlinear system, which I will soon define. So first we will define what is periodic solutions. So we have again x dot is equal to f of x, right? So solution repeats itself. I mean, it comes back to its from where it started for every t which is strictly greater than 0. Right? The solution repeats itself, right? Every after a period of capital T seconds, right? Why is this strictly greater than 0? Yeah? Yeah, but why can't it be greater than or equal to 0? What is it? So when does that happen? It's an equilibrium point. So to rule out equilibrium points, so equilibrium points are trivially periodic solutions, because if you start at equilibrium point, you will continue to stay at that, right? To rule out that, we take t to be strictly positive, right? Well, example, the simple harmonic oscillator. I mean, harmonic oscillator, there's nothing simple about that. Or the linear harmonic oscillator. x1 dot is x2, x2 dot is minus x1, right? So how does the phase portrait for this system look? They will be all closed orbits. There will be continuum of orbits, closed orbits. This sense is x1 dot is plus and then x2 dot is, yeah, correct. So this sense is correct. Even though I have marked all these orbits or the trajectories spaced out, you give me any initial condition, there is a closed trajectory corresponding to that. What does this mean physically? You give me any pendulum initial condition, right? There will be one trajectory corresponding to that. You put a bit epsilon this, there is another one which is close to that. So they all corresponds to the closed trajectories, right? So in our analysis, we are not interested in the shape, whether it's a circle or a ellipse or distorted circle. That is not of importance to us. What is important is whether it is closed, right? So these are called periodic solutions. Okay, so these are precisely periodic solutions. What is unique to nonlinear system is, in nonlinear system, you could have isolated periodic solutions, which you will never find in linear system, right? So we have a special name for that. They go by limit cycles. What is meant by isolated? You can find a neighborhood of that closed solution such that in that neighborhood there is no other closed solution, right? Unlike this one, you give me any neighborhood of this, a point, you take a point, you give me any other, there is always another trajectory that is periodic solution which is in that neighborhood or which is sort of intersecting. Or if you want to talk about neighborhood in the sense some ball like this, right? And you take a point, right? You get a periodic solution passing through that, but that is not the only one, right? There are others also sitting in that, right? So isolated means there is only, at least you can find a neighborhood such that in that neighborhood there is only one periodic solution, right? Such periodic solutions are called limit cycles, right? The limit cycles are something unique to nonlinear systems. You don't find that in linear system. In linear system, you will get always continuum of periodic solutions. In fact, this is called continuum. Okay. Now, question is, how do I find whether it has a nonlinear system has a periodic solution, right? Or how do I know whether it doesn't have a periodic solution? What are the tools? Okay. So certainly linearization is not a tool. Why? Because it will throw up at those equilibrium point, it will throw up maybe, I don't know, no, it will not throw up eigenvalues which are j omega axis, but what does linearization say? It only, we know that we cannot use the linearization when it is a center, right? And in all other cases, they are not periodic solution. The saddle, the focus and all, they are not periodic, right? So linearization fails to answer this question, okay? So we need something different, right? So this is a famous oscillator known as the van der Pol oscillator, right? So the requirement of a good oscillator should be that its amplitude should not be, it should be robust to any perturbations. Okay, that is one requirement. And you need a oscillator which caters to your frequency, to some frequency of oscillation, right? Now that you cannot get through a linear oscillator. And the other thing is, you can never construct a linear oscillator. It is impossible to construct a linear oscillator, right? Because non-linearities are inherently there. Okay, so that motivates to study this nonlinear oscillator. This is a nonlinear oscillator which has a nice properties, that is, whose amplitude of oscillation is independent of the system parameter. For example, here you can think of epsilon as a system parameter. This could be some L, C or something like that of your circuit, right? So it is robust to that. What it at most does is it just distorts the shape of your solution, right? And it is independent of the amplitude is independent of this choice of this epsilon. So let us analyze this. So the system has only one equilibrium point, and if you do the linearization, this origin is unstable focus. Okay, and the phase portrait looks something like that. So you will have some okay. So this is the limit cycle, and all trajectories starting close to the equilibrium point, they will all spiral to rather I will draw a vector field because that will be very confusing. So this is either unstable node or focus. I mean, this doesn't matter. What is important is this, right? So all the vector fields will, if you perturb it near this, they will go away from the origin, right? And they will be all okay. They will all approach this limit cycle, and any trajectory outside, okay, they will all also approach this limit cycle. They will never hit it in finite time. They will all be approaching to it, right? So this is a very famous example. It's a van der Pol oscillator called the van der Pol oscillator, and it exhibits a limit cycle. Okay, so please always don't forget to mark the orientation. Okay, if you don't mark the orientation, it's a equilibrium set, right? So this is a limit cycle, right? So the robustness here is any perturbations, right, about this limit cycle. That means if you perturb it, where will it go? It will come back. You either perturb this side or you perturb this side, right? That is the robustness, right, which is not possible in a linear oscillator. Why? If you perturb it, it will go to another periodic oscillator. You design the oscillator for a one periodic solution, right? But if there are perturbations, it is going to another periodic solution. That means it is not robust. Whereas here, you designed it for one periodic solution. If you do perturbation, it will approach this periodic solution, of course, eventually it will approach. Okay, not infinite, right? So that is the the nice thing about this van der Pol oscillator. Okay. Now the question is, given this nonlinear equation, right, how do I infer existence or non-existence of periodic solutions? Okay, there are no results for the existence or non-existence of limit cycle. There are only results for the existence and non-existence of periodic solutions. You may say, why? I mean, if I say if it doesn't exist, I mean, why there are two separate set of conditions? Well, because they are both sufficient conditions. So we'll see there is a set of sufficient condition to rule out the existence of periodic solution, then another set of sufficient conditions to rule in the existence of periodic solutions. Okay. So the first one, to rule in the existence of again, all this is applied for second order system, R2, okay, and so we have only sufficient conditions. That means if those conditions hold, you can say periodic solution exists. If they don't hold, you cannot comment anything. Okay. So the first one is called the Poincaré-Bendixsen's criteria. So first is yeah, so it's called let P be a closed and bounded subset of R2, right? We saw open set, the definition, right, like a ball without the boundary. So you take points along with the boundary, right? That means points all in the set along with the boundary, it becomes a closed set, and it is a bounded set if you can enclose that whole set in some ball of some radius and some center. Okay, so for example, in the real line, right, the intervals are closed sets and also bounded sets. Okay. So you require a subset P to be a closed and bounded set, then and P contains no equilibrium points or if it contains, then they are unstable or unstable node or focus. So what is the first condition? You need you take a region, right? So that is like your candidate region, right? You want to say, well, I want to test whether in this closed and bounded region whether there are periodic solutions, right? So in doing so, that you first check whether it has equilibrium points. If there are no equilibrium points, fine. If there are equilibrium points, or if there's an equilibrium point, okay, then it has to be either an unstable node or unstable focus, right? If there is a saddle, then you cannot apply this criteria. I mean, the you can no longer proceed with this criteria, right? So once you have this, right, and if you show that P is positively invariant, right, then these two together will imply that P contains periodic solutions. As I said, it doesn't talk anything about limit cycles, it only talks about periodic solutions. So the existence of periodic solutions is guaranteed by the if the Poincare-Bendixson's criteria hold, right? That means if you have a closed and bounded set. So for example, in this case, think of this to be the P, right? It's a closed and bounded set. It contains an equilibrium point, which is an unstable node or focus, whatever it is. And if you see all the vector fields, right, where are they? They're all pointing inside. You look at the boundary of P, right? Where do the vector fields point? Is there a vector field which is pointing away? No. So it is invariant set. That means all the trajectories, if once they come into P, they are trapped forever. They cannot escape out, right? So it's an invariant set. So by Poincare-Bendixson's theorem, this region P has a periodic solution. The only thing is, through phase portrait, you actually concluded it has a limit cycle, but that is another analysis, right? So this analysis will only tell that the P contains periodic solutions, right? This is how you apply the criteria. The hard part is, oh well, this was second order system. I could draw the phase portrait and say that P is positively invariant. But in general, the hard part is showing how do you show the positive invariance of a set, right? And as I said, it again popped up here, the notion of positive invariance, right? And then, so this is, as I said, this is sufficient condition. If this fails, you cannot conclude anything, right? So then there is also a sufficient condition for the non-existence of periodic solution. So again, this is restricted to again a second order system. Okay. So you need here a simply connected. So without going to the much math things, I'll just tell you what has to be, what is required for this. So it goes by a name called Bendixson's criteria. And then So the ingredient that you require is a simply connected region. Think of simply connected region is a region with no holes in it, right? For example, the annular ring. This is not simply connected because there is a hole here, right? Whereas the disk, this is a simply connected region, right? Of course, there's more math to it, but I skipped all that, and through some pictures I could explain what is meant by a simply connected region, right? So you have a candidate set which is a simply connected region, and in that calculate the divergence of f, right? So what is this divergence? This is dou f1 by dou x1 plus dou f2 by dou x2. This should not be identically equal to 0 and change sign in that D. If it satisfies that, then that region has no periodic solutions, right? So let us see through an example. So in fact, this is easier to check because it just requires computation of this. So let us calculate the divergence of f, which is nothing but here x2 square, and this is with respect to x1, right? So this is not identically equal to 0, right? And this is always positive for all x not equal to 0, right? So this is so it satisfies the hypothesis of the Bendixson's criteria that the divergence is not identically equal to 0 and it doesn't change sign, right? So sign changing means from positive to negative. In some at some x it should change sign, right? It is not changing sign, right? So I mean this is true for all of R2, right? The set D can be chosen to be the whole of R2 because whole of R2 is a simply connected region, right? I mean for this system, okay. You can see more examples in my lecture notes, where there are some examples where this fails also. So you can't conclude anything because they are all sufficient conditions. Okay. So yeah, that almost finishes today's whatever I want. Huh? No, it does not have. So this one is, it is not identically equal to 0, okay, because it is x1 square plus x2 square. It's not there is something here, right? And it doesn't change sign. It is always non-negative. Non-negative. Yeah. So tomorrow afternoon we'll do the stability part. Okay. Morning, Professor Umesh will carry on. We'll stop for here.